6.2 Inverse functions. To start, let's refresh on a few things. A relation is when we have x and y values paired together as in coordinate points, x comma y. Okay? An inverse relation is when we would switch those x and y values. For example, in an original relation, we would have the points 0, 6, 1, 4, 2, 2, etc. In an inverse relation, we would just switch the x and y values. So now we would have 6, 0, 4, 1, 2, 2, etc. Okay, now that's for an inverse relation. If we wanted to find an inverse function, we're going to switch the actual x and y variable in the function, and then we're going to rearrange that equation to solve for y. Let me show you what I mean. Let's say we want to find the inverse of the function y equals x plus 4. We're going to start by switching the x and the y. Now we have x equals y plus 4, and at this point, we want to rearrange for y. Meaning we want to get the y by itself by moving this 4 to the other side, so it returns to y equals. Now with functions or inverse functions, a lot of times they'll put this -1 on the top. Okay, so you might see it written like this. It doesn't mean move that y to the bottom, it just means it's the inverse of what we started with. So this function here and this function up here are inverses, and there's a few things about inverse functions that we should know. So to start, graphed here is the line y equals x. It goes through the origin and it goes up 1 over 1. And here we have the line for our original equation, y equals x plus 4. If we graph that with the inverse function, we can see it's symmetrical around the line y equals x. That will always be true. Another thing that's always true is if we were to take one of these equations and plug it into its inverse. So let's say we took this and we plug it in up here. We'll always get the same thing. So I'm taking this x minus 4, putting it in for that x. The 4's would cancel out, and we're left with x. Okay, it doesn't matter if we do the opposite. Okay, it went from this way. Plug this in for that x down there. Again, 4's would cancel, and we're left with x. Let's say we have the function f of x equals 2x minus 1. You should know that the y is really just this f of x, so when we switch the x and the y, the x goes where that f of x is. All right, so now we want to rearrange this equation to solve for y. So we're going to add 1. Once we do that, we have x plus 1 over here equals 2y. We divide both sides by 2, and that's going to give us our inverse function. All right, x plus 1 over 2. If we graph it, so our original equation, 2x minus 1, starts at -1, goes up 2 over 1. Our new equation, okay, would start at 1/2, and it's going to go up 1 over 2. Okay, again, we can see it's symmetrical all around that red line, y equals x. If we took one of these and plugged it into the other one, let's start by taking this first one here, and it's going to getting crowded with all this marker on here, but if we take x plus 1 over 2 and we plug it in for this x, okay, we would have 2, and then in place of that x plus 1 over 2, 2's would cancel. We'd be left with this, minus 1, 1's would cancel, and we'd have an x left. Okay, if we went in the reverse order, same thing happens, everything cancels, and we just have an x. This always happens with inverse functions. Let's do one last one. F of x equals 2x plus 4. Switch the x and the y. Rearrange it. We'd get an inverse function of x minus 4 over 2. If you're asked to graph it, we should see it symmetrical around this line y equals x. So the original function graphed, 2x plus 4, would start at 4, goes up 2 over 1. Our new function would start at -2, go up 1 over 2. Okay, again, we see it's symmetrical around that line. And if we were to plug in either of these functions into the other, we see 2's would cancel. After that, our 4's would cancel. Or on this side, our 4's would cancel first, leaving 2x over 2, okay, giving us x when we simplify it. The last type of question that you might get in this section is when it gives you a graph and it says, is this graph a function? And along with that is the inverse of this graph of function, right? So let's say if we have a graph of a parabola. Now we can tell if this graph is a function by the vertical line test. So we draw a line straight up and down, and if it hits this graph just once, the graph's a function. Okay, we're looking to see, is there anywhere we can draw a vertical line and hit the graph more than once? If so, it's not a function. So the answer to this first question is yes, this graph is a function. Now, is the inverse of this graph a function? So the inverse is going to be symmetrical around the line y equals x. So if we graphed this, it would look something like that. All right, and if we did the vertical line test on this, we would see pretty much anywhere we draw the line, we're going to hit this graph 2 times. So no, the inverse is not a function. Now the shortcut to this is from that black graph before we did the inverse around that line y equals x, we can do a horizontal line test. If we draw a horizontal line and we hit the graph more than once, okay, and if we can do that anywhere on the graph, the inverse is not a function. So let's say we have this graph. So to start, is the graph a function? Okay, is there anywhere we can draw a vertical line and hit it more than once? There's not, so yes, this graph is a function. Is the inverse a function? Can we draw a horizontal line anywhere and hit it more than once? Okay, we can't do that anywhere either, so yes, the inverse of this graph is also a function. Now let's say we have one of these W-shaped graphs. Okay, this would pass the vertical line test. There's no place we can hit it more than once with a vertical line. All right, however, a horizontal line, we can hit it more than once. Here we can hit it twice. Down here we could actually hit it 4 times. So the original graph, yes, is a function, but no, the inverse is not a function because it fails that horizontal line test.